Welcome to PCB Chat, where we talk with experts across the printed circuit design, manufacturing, and electronic supply chain fields. I'm Mike Buteau, Editor-in-Chief of PCD&F and Circuits Assembly. First, a word from today's sponsor. This podcast is sponsored by PCB East, the original conference and exhibition for printed circuit board design, fabrication, and assembly on the East Coast. Circle your calendars for June 15th to 17th in Marlborough, Massachusetts. Visit the website at pcbeast.com for information. My guests today are Keshav Amla, founder and CEO of Avishtech, and Tarun Amla, co-founder and CTO. Avishtech is a San Jose, California-based developer of simulation and design software, specifically Stackup and 2D field solvers. Gentlemen, welcome to PCB Chat.
Thank you.
More than I can ever recall, design engineers are paying close attention to materials. It's not just about the routing anymore. And I want to talk with you about your latest software release in a moment. First, however, let's talk about Avishtech. Keshav, you launched the company while you were at Stanford, correct?
That is correct, Mike.
So why don't you tell me a little bit about what gave you the idea and what was the motivation?
It all started in 2015 when I was at Stanford. I'd just joined for my master's degree at the time, and so Avishtech was going to serve as the vehicle within which I would start my own company. And this would be initially there were some ideas I had as related to autonomous driving IP. And so we went ahead, Tarun and I went ahead, we filed patents, and those have since been granted. And those are things that are still ongoing. About a year and a half ago, it seemed that the opportunity was ripe for us to really innovate in the EDA sector in a very meaningful way. And that's because what we could do was we could blend our deep knowledge of mechanical engineering, material science and engineering, electrical engineering, and advanced numerical mathematics, and really use that to leverage all of that to create an integrated environment where you can now design PCBs not just for signal integrity or not just for one particular attribute, but really look at the whole picture. And we were uniquely poised to do that. And so that's why we decided that we should go ahead and build an advanced 2D field solver that'll have the highest accuracy possible for impedance, loss, RLGC, all these parameters. And also, hand in hand with that, we would build a Stackup design and simulation tool where now you can actually look at the thermomechanical simulations, you can look at the reliability, the manufacturability. And now, especially since the industry has gotten to the point where you don't really have the wiggle room that you used to have, especially as you're getting into the high data rate and high frequency applications. I mean, when you're trying to do 112 gigabits per second per channel, or if for 5G applications you're getting up to 28 gigahertz, you just don't have that headroom that you used to have. And so now, where the previous solutions would have been maybe not 100% accurate, but if they tell you it'll work, it would work. Now, even that binary question of, is this design going to work for my needs? Your software is telling you yes. And then when you go to build it, you find out that the answer is actually no. And so that's why it's become extremely critical to get the modeling right. And so we saw an opportunity to not only do the modeling right on the signal integrity side, but also to enable a completely new set of modeling and simulation as relates to reliability and manufacturability that wasn't possible in the past. And so when we saw this opportunity and as we started working on it, we realized that we were really onto something here. And that's how we went about it.
Was your master's in EE?
So my undergrad was in mechanical engineering. So I studied at Caltech and earned that degree a few years ago. And then at Stanford, I went to pursue my master's in material science and engineering. In fact, I had then continued on to a PhD in mechanical engineering there. However, I left the program when when we started working on our Gauss tool sets, that's when I decided that I needed to focus on this full time and really throw myself at this effort. And so then I left the PhD program.
And Tarun, you have a long experience in printed circuit board laminates. I'm sure most of our listeners will recognize your name. Did you influence Keshav's focus on board level materials?
Yes, I think to a large extent, I did. We talked about some of the problems that we encountered in PCB design, and it seemed like there was a lack of understanding of certain basic principles, and there was this confusion about what was right and what wasn't, and there were schools of thought. There wasn't any science being applied to it. And that's where teaming up with Keshav really brought that to fore. On the electrical engineering side, I'd done a lot of modeling work prior to this. And then it was just taking that and the thermomechanical properties that we were developing. It just seemed right for us to move in this direction because his skill set is complementary to mine. When I can do work on numerical simulations, he can help with the coding part of making the design interface. So a lot of complementary skills. So if I was looking for a partner, I couldn't find a better one. And so when we talked about these problems, it was his idea that we should start working in this direction and try to distill all this knowledge base that we have internally and the complementary skill sets and move forward with something that's going to be beneficial to the industry. So I think he influenced me, I influenced him. So it was a lot of discussions we had around this topic that kind of fostered the vision of what Avishtech's doing right now.
How can Avishtech help design engineers understand their stack-ups? Is it just a matter of having the most extensive materials library?
It's not the materials library because that's just data. It doesn't do anything in terms of telling you if the design is going to be okay or not. So there's a perception out there that the materials that are being used are no different from other materials that are being used. For instance, copper, well, it's a metal. Well, steel, it's a metal. And then laminate, well, it should have one set of properties, but that's not the case. Every stack of design that's done is different. And the difference in properties can be as high as 50%. So certain properties can change 50, 60% from what you might have your baseline on or what the data sheet's publishing. So the whole point was, how do we get that information out? Because when you look at the data sheets, they just publish one number. And a lot of times people think that that's the number that's going to stay with their stack up. So if someone says your coefficient of thermal expansion is going to be 40 parts per million, they expect it to be the same for all stack-ups. But that could be 95 in another one, and 105 in the third one, and maybe 28 in a third one, in a fourth one. So basically, that's the thing that designers don't understand. They think it's a material, so how different could it be? But it's a composite, and that's where all the properties depend on the ratio of the resin and the glass. And how do you distill it down into numbers and then into data that can be looked at and say, well, this is a design that's not going to work, and this is a design that's going to work. So that's where we put in a lot of effort to take the information that's provided from the material supplier, and from that extract the properties that we think that we believe are very important inputs to those reliability decisions and modeling. So it's not just the dielectric library, because that doesn't do anything except for providing dielectric numbers. But taking that and saying, okay, my whole stack up, what it's going to do in terms of thermomechanical properties, that's the key thing. And then once you get those properties, we then don't want people to spend days and months and years modeling that on finite element analysis. We give them the answer with that and say, well, this is going to survive maybe 1,000 cycles between 25 degrees and 150 degrees C. So that's the difference, that it's intelligent extraction of data and converting it into information that the user can see without having to delve into the minutia or the details of how, because you can't get that data from the suppliers in any case, because some don't have capability, some don't have the understanding, and some don't want to give it. So that's what we have done here.
And just to add on to that, of course, we do start with that extraction of the relevant inputs for our simulations. But another very critical side of it is that the simulations that we conduct, they are for woven composites. And if you try to model composites, as was just mentioned, if you try to model them as if they're similar materials to, say, a semiconductor or some other pure elemental material out there, you're not going to be able to get the kind of detailed information that you need, simply because woven composites behave very differently. And modeling of woven composites is a significant challenge, especially if you're trying to do it within the context of a lot of the other kinds of simulation approaches. But that's something that we have gone ahead and done. And so now, once we extract the relevant inputs, we then run them through our simulation. And so with our library, we have the relevant inputs already in our tool, ready to go. And so then, when you specify your stackup, it runs a simulation on that stackup and tells you exactly, as was just mentioned, that okay, this stackup, you're going to see that the Z expansion is 28 parts per million below TG, but on the next one you'll see that 95. And that's because you're going to specify your particular stackup, and it's going to run an actual simulation on the particular configuration that you have. While everything starts with data, it goes from data to relevant inputs to a simulation, and then we don't even stop there. We actually then tell you what all of that means. I mean, so okay, these are my CTEs and moduli that you've told me that my board will have. But what does that mean for me at the end of the day? Am I going to see the problems that I'm trying to avoid, or is this design going to work for my needs?
You've mentioned the relevant inputs. What are some of those, and where do those inputs come from? You mentioned that you already have them embedded in. So, how are you deciding what goes in? And following along what Tarun had mentioned, the laminate supplier or the material supplier may not give you exactly what you need to know. So, how do you derive that?
That's something that we've developed this algorithm to do that. So it's more like, I mean, if you look at, for instance, the noise signature of a submarine, you can build a submarine if you have the right data, because you look at the turbulence and you kind of look at that information, you build it. So that sounds like a more esoteric example. But when you make something, well, the first thing you do is kind of look at what the density of the material is. From the density, you would draw, based on the knowledge we have, that what kind of filler percentage it might have. And from that, you can get the neat resin DK and DF. And when you get these properties, there are models that you can use to then build it. And like all models are wrong, some are useful. What we then
George Bach.
did was, in this case, was yeah, George Fox. So then what you do is you go out there and see, well, how useful is this model? So that's where what we did was we did a lot of extensive testing on this. We built random boards where we asked the PCB manufacturer to kind of go and build it on a material of their choice, just tell us what it is. And once we got that, we sent it out, spent a lot of money for its testing. And once we got that data back, we compared it to our results, and it was right on target, very, very close. And for this kind of testing, since there's not a lot of alternatives available as to how to get the data, there are some proxies. For instance, if you don't really know the z-axis modulus, well, the expansion is a good measure, a very close proxy for it, a good surrogate in terms of being able to predict what the moduli will be. So that's what we did in this case. And again, same thing on the electrical side. We looked at the impedance and compared it to the numbers that had been published in literature, where there are closed form solutions available. conformal mapping dating back to the 1940s. So we compared those numbers to what we got with our simulations without tuning, without doing any of those things. So most of our coding work was completed very early on. I think last 1 year, we've been spending a lot of time and money on validation because we didn't want a tool that just kind of gave the almost right answer. We wanted to give as close an answer as possible. So that's where a lot of effort went into, was the validation part of it. So those numbers that we're talking about are at the neat resin level, at the pure resin level. And then the properties of the glass, those of course are available in literature. And then combining them, that's where micromechanics comes into play. And that's what we did.
And curiously, the approach that we're talking about that we're enabling for our users, that by using our tools, they'll be able to design for their needs correctly the first time, and then when they have to go and build physical boards, do actual validation. That's going to be the goal, is that they just have to do that once, right? I mean, they don't have to keep doing constant respins. That's actually very similar to the approach that we used in developing this software also, that everything we did came from a solid basis in physics. And so as a result of that, what we did was we made sure that we created the correct models, and we were very thorough in building our simulation approach. And so then when it came time to test, we were getting confirmation that that what we've done is correct, rather than having to see, okay, well, the numbers are very off, and now we have to go and go back to the drawing board. We use that same systematic approach that we're trying to enable for our users in the development as well.
What are some of the mechanical properties that the algorithm can help spit out?
As far as what we require for the inputs, the algorithm that we develop for extraction, it gives us those polymer properties that Tarun just spoke to. But as far as what our users will be able to get when they construct a Stackup design and click the compute button, what they're going to get are CTEs in all three directions, X, Y, and Z, as well as below and above TG for the Z. And they're also going to get the Young's moduli, shear moduli, and Poisson's ratios in all three directions. So those are the thermomechanical properties that they get. They also get a warpage number, which is going to be 0 for a balanced, symmetric design. But if you're doing something that's asymmetric, working with some kind of a hybrid construction, you're likely to see warpage. And so this will also provide that information. And Tarun, did you want to speak to anything else on that?
Yeah, there is the glass stop, which I think is the major problem, that a number of times designs fail because when the test vehicle was used, a certain construction was used, and when it was used in the field for a design, the numbers changed. For instead of 1 ounce, somebody used 2 ounce copper, and instead of using a certain construction, they changed it because it cost less or was more appropriate or readily available. And then what happens is resin starvation or glass stop. And that's something that nobody pays attention to. There are some, laminate manufacturers which have in-house tools, but nobody gets to use them because the stackups are done independently of that. And so what happens is when they design the product, they don't see the glass stop. And a designer may just optimize a design for, not optimize, actually just maximize, for instance, for signal integrity. And then find out, well, this is not even buildable because they're seeing issues with glass stop, which leads to CAF or crazing or major voiding. And that's one of the things that we've seen validated. In fact, one of our first few customers came back and said, well, this predicted what we actually saw in the field after a long time. So to us, that was a great validation that it could do that. So that's one of the things that's overlooked quite often. And this does require finding out, for instance, if it's a heavily filled system that's coming from someone, then it doesn't have the capability to fill those traces and the gaps between those traces. So that's the other thing that it does. And then once you get the mechanical properties, then it can give you predictions for solder joint reliability based on the package size. It can give you PTH reliability numbers based on, again, the hole size and the pitch. And again, these are median numbers that you get, but again, grounded in science and fairly accurate so far with the validation we've done.
So GaussTech has the advantage of enabling the user to predict the failure modes at the Stackup design stage. As I understand it, that's novel. Can you tell us a little bit more about how you do this?
That's exactly what GaussStack was designed to do, and how it does this is through this additional simulation capability. The fact is that you have a single environment within which you construct your stack up. You press it, you click compute and get the pressed thickness, which will then be used as an input for as the relevant thickness for your electromagnetic simulations, for your impedance analysis and synthesis, which is another capability that we offer, where you can specify for the entire stack up what your target impedances are, and it will find that solution for you for all of your single-ended and differential traces all across your stack up, no matter if it's a 10-layer board or a 100-layer board. So that we have that electromagnetic side of the simulation capability. But in addition to that, we have the ability to look at the manufacturability checks. So am I going to have glass top in this, which is a key issue if you need to avoid calf, you want to avoid issues with voiding, crazing, all kinds of things that are going to prevent your board from even being manufactured, and also reduce the life in service, assuming it is capable of being manufactured, even though it may be a marginal case. So you're able to check for manufacturability, and you find out, okay, this design is going to give me glass top, and you'll often find that the difference in terms of a stack up that passes all of your checks and one that's going to fail could be something as simple as just changing a glass style or going to a higher resin content construction. The fixes are usually not very complicated, but they're fixes that you wouldn't be able to find with just a rule of thumb, or if you don't have an environment that can tell you what to look for. So first thing you're going to do is when you use Gauss Stack is, rather than just you've designed your stack up because you're looking for a particular set of thicknesses, and you just jump right into your signal integrity analysis. What you're going to do with Gauss Stack is you're going to first check and see, is this board manufacturable? Am I going to have calf issues? Am I going to have crazing and voiding issues? Then you're going to see, okay, well, is this board going to be reliable? Is it going to pass reflow? Is it going to give me enough cycles to failure for my plated through holes or my microvias or my solder joints? And once you now have a design that works for that, then you're going to see, well, is this going to be sufficient from the signal integrity side of things? Now you have the ability to look at that complete picture at the stack up design stage, rather than only finding about some problems when you build a prototype of your design, when you make a test vehicle a few months down the road, or even worse, if you're seeing field failures much later on. And so that's where Gauss Stack allows you to, rather than doing this constant prototype respin process, it allows you to go to market faster. It allows you to catch these problems and fix them before you're tied down to a particular design.
I'm very interested in the idea that you can predict solder joint reliability based on the stack up, right? I mean, that I've never run into that before.
Right. I mean, that's something that has been attempted to a certain extent, but the traditional approach has been that, well, let's run a finite element analysis on it. But the biggest issue there is when you run the finite element analysis, you're basically doing the exact same thing, that we'd be doing unless there are some areas where you have stress concentration. An analytical solution is better than a finite element solution. But the inputs that you need for the FEA, where do you get them? And that's the issue. So, in my several years trying to do some modeling work, that was the issue. Where do you get those inputs? And basically, the kind of tool we have, even if you wanted to do an FEA simulation, which why would you do that? Because you just run one cycle, find out what the plastic strain is or the strain energy is, and then apply a formula. Well, you can do that unless you have areas of stress concentration on the board itself. You can do that fairly easily now that you have those properties, because what you need for essentially for doing that is what is the modulus of the board in X and Y, and what is the CTE. If you have these two numbers, and then you know the pitch of your solder balls, and you basically also know the dimensions of the package that's being used, then it's a simple mathematical calculation. But if you don't have those inputs, then it's going to be garbage in, garbage out, because those numbers affect it to a very large extent. And so that's the input that you basically need. That you might have that properties, for instance, for one layer, but for the entire Stackup, highly accurate numbers are what you need to predict solder joint reliability. And those are. I think there are other people also have tried doing that, but more at the level of running FEA simulations on it, where the inputs are missing, right? So your inputs are at best going to be estimates that you would generate from some data sheet, but it's not going to be representative of a Stackup. So each stack will have a different reliability number, maybe not that huge a range, but it could be pretty large. We see some simulations where we see like 300-400 cycle difference between one stack and the other, and all you might have done is changed one or two components in it, one or two layers in it.
And so even if you did want to do that FEA simulation, you would still need the thermomechanical properties that you get from Gauss stack. People are welcome to still do it that way if that's the approach they're used to. But the purpose here is to get you to the answer accurately and quickly. And so what you'll find is that if you were to, now you had these inputs, again, you still would struggle to run a case to failure, simply because doing that kind of elastic plastic analysis in finite element tools is an extreme challenge, and that kind of modeling and simulation takes many months, if not longer, to do. Which is why we have that capability in Gauss stack itself. And you'll find that your results, yes, with the FEA, you'd still get a reasonably accurate result, but it's going to be consistent with the result that you would get from the prediction directly from Gauss stack, and you don't have to spend all that time and effort trying to get it to work, because all of the inputs that you need are there, and our approach is different. Our approach is one that enables it for people without having to. I mean, ease of use is really one of the things that we've emphasized in our tool sets, and we just want to make sure that our users are able to get the information that they care about without having to become experts in a particular method and experts within our tool set. You should be able to get running with our software very quickly, and be able to get all of the information that you need.
The tool does account for ground plane losses, and which is something pretty major that, when you're running simulations, there is a false sense of security with other tools where they say, well, there is another 20-30% headroom if you want to go to 112 gigabits per second, right? And that's not a reality, because that's all being taken up by the copper losses in the ground plane. So that's, unfortunately, everyone's talked about it, but none of the tools included except ours for the first time. And so that's something that is important, that when we were asking about some of the failure modes. This is something that designers can and OEMs can observe after the fact, after they've designed it or after they've simulated. They'll find that it doesn't work because it doesn't include one major thing, that's the ground plane losses, which, back in the day when you were running megahertz was fine. But now you're running at 28 gigahertz, and the difference between the distance between the ground plane and the signal layer is 4 mils, 100 microns. And those proximity effects can be as high as 35%.
Can users manipulate or otherwise edit the library to reflect their own real-life results?
For dielectric properties, yes. So that was one of the questions that we've had to field, is that, my personal experience is that material from vendor A actually has the dielectric constant as 3.5, and what you have in here from is 3.2. So yes, you can change that. Those are the things you can do. If, for instance, you have the conductivity numbers, for instance, we're building a library which you can just go to the copper supplier and pick it up and say, well, this copper has a conductivity which this was data that was never available, but that's some of the vendors are supplying it to us. And you could say, well, it's 99% of copper, and the other copper is 90% of the copper. And then then the user might say, well, my experience is that the roughness is not really 0.4 microns, it's like 0.2 microns. Well, they can plug it in. So that's the capability that they have to change those inputs. Now, for the mechanical properties, they can't do that because we don't make them visible to the user. And again, it's a level of sophistication that be required to do that. So we're keeping that away. But for instance, on PTH reliability, what we are predicting is that there are no manufacturing inconsistencies or variability. So that is not included in our simulation. And then someone who's a sophisticated user might feel, well, my copper modulus is not exactly 117 GPa. I have this data and it's like 95 or 50. So they can plug that number in. And they say, well, my copper ductility is not 27%, it's 35%. They can plug that number in. So that can be done, but we put defaults in there which are representative of what the industry is doing. So there may be shops that are better than this, and they can specify that and say, well, no, actually, our copper ductility is higher and our modulus is more consistent and it's higher. Then, of course, they'll get different numbers on their simulation. So that capability we've allowed. But it will take, unfortunately, that data is also not very easily available because copper ductility, you just don't have direct numbers on that. So we provide them that capability, though, to modify the numbers.
And is that cloud-based or is that a local library?
It's embedded in the tool itself.
So it's client.
It's a local library.
Yeah. Now, this is interesting. Lee Ritchey, whom most listeners will know as one of the leading experts in signal integrity and PCB design, is actually endorsing GaussStack. How did that come about?
That was something that we have been talking to him. We sent him, we engaged with him very early on, and we sent him trial versions of the license, and he gave us some very important feedback, especially relating to the library, relating to some of the other things that he wanted to see in there. So in ways, he helped us to get to a more sophisticated version. But then there was this benchmark case that he had, which he asked us to work on. And that did require us to kind of modify the tool in a way that you could do those measurements in situ and not have to kind of change from one tool to the other. But these were actual measurements, and he asked us to simulate those. And there was very close agreement on that. And we had several presentations with him where he was involved listening to the tools. There were tough questions as usual. And so we're very pleased to get his endorsement. I mean, that was a huge win for us. And we are really thankful we got it because we had to go through his process of making sure that he was satisfied with the results. So we engaged with him fairly earlier on.
Key to that was building that functionality that he would want to see in a tool. A lot of some things that he hadn't seen in competitive offerings, and then like Tarun just said, for his benchmark, he wanted us to provide the the results for signal integrity, and they were exactly in line with what they should be. And on top of that, we built the functionality that allows you to run that in a completely integrated fashion. And so we added that functionality to accommodate that kind of a benchmark as well. We worked hard on that, and we just wanted to make sure that we addressed all of the points that he wanted in there, and we're really pleased because we, like most in the industry, have a very high opinion of Lee, and are really pleased that he also holds in high enough regard to give us his endorsement.
And we haven't really talked about Gauss 2D, which is your field solver, but that's already been available for at least a year or so, right?
Yes, actually, both Gauss 2D and Gauss Stack have been available and in the market. However, what we're doing now is that we've really revamped everything to the point where this is now in the form in which we want it to go wide, and want the entire market to know, because we've been working very hard on building a lot of capabilities to take this well beyond what's out there. And so when we originally launched our products, we built a very powerful framework. In the time since, we've made it so that not only does it have this extremely powerful engine, but it's something that customers can use in ways they couldn't have before, because we have that fully integrated library, because we have put in a lot of effort to validate additional approaches, additional things we're doing, and really make this a tool that's basically a drop in for our customers. They don't need to go and hunt for new data, hunt for new things. But yes, to your question about Gauss 2D, the field solving capability of that is actually also the basis for the field solving capability in Gauss Stack. They share that same engine. But Gauss 2D, being a more signal integrity focused tool, also has some more detail as pertains to those kinds of that kind of behavior, where you can look at your S parameters, where you can look at things like crosstalk, where you can look at power handling capability for microstrips, and you can also deal with some more esoteric cases. You can put in shielding. You can account for coplanar waveguides, multi-conductor buses of microstrips and strip lines, and so that's so the way we have our process in mind is that Gauss Stack would be the first step in your process, and then once you've figured out what your Stackup is going to be, you can also make sure that it's good from a signal integrity standpoint within Gauss Stack. But for people working with transmission lines, once that Stackup has been figured out, then you can go to Gauss 2D and use that for more detailed analysis, and really look at all of the properties that you would care about, and look at it and have a completely frequency dependent kind of tool for you to use in that environment.
And listeners should know that the Avishtech website at Avishtech has quite a bit of information and some videos as well that you kind of walk into some detail explaining how the tools work.
Yes, exactly. We go through how you go about using it, and try to give you insights as to what this would look like in deployed in your organization.
Now, Keshav, has your father ever happened to mention that he appeared on the cover of our magazine some years ago?
Yes, I actually I have a copy of that magazine with me.
We made a life-size version of that for him, right? He has that still in his house.
Yeah,
right?
that was.
So it's notable because there's really not a whole lot of people that have been on the cover of our magazine. So it actually was kind of a big deal.
Oh, it is for me. I've kind of kept that copy, and then I found out that when I was messing, it was with him, so with Keshav. So yeah, so no, very proud of that.
Great. Well, gentlemen, I truly appreciate you taking the time to speak with me today on PCB Chat and to give a little bit more background on the company and also the tools. Keshav, as I understand it, the company name has it's not just a random word. There's actually a genesis to that. Can you explain it?
Certainly. Avishtech it's a portmanteau word. It's a combination of two words, but from two different languages. So the second part, tech, everyone would realize that that's from technology. But the first part of it comes from the Sanskrit word avishkar, which means invention. And so basically, this was that blending of innovation, but innovation brought into a real tangible form in terms of technology. And that's really what our vision is to make serious significant innovations, but make them a reality, make them in tools and products that people can use, rather than just some intangible idea.
Well, that's a great story to close us out on. I'd like to thank my guests today, Keshav and Tarun Amla of Avishtech, and remind listeners that today's podcast has been sponsored by PCB East, the original conference and exhibition for printed circuit board design, fabrication, and assembly on the East Coast. This year's show takes place June 15 to 17 in Marlborough, Massachusetts. The website is pcbeast.com. For PCB Chat, this is Mike Buteau. Have a nice day.